Section 14.8, Lagrange Multipliers. To find the maximum and minimum values of f of x, y, z subject to the constraint g of x, y, z equals constant k, assuming that these extreme values exist and del g, the gradient of g on the surface g of x, y, z equals k, then you find all values of x, y, z and lambda such that del f, the gradient of f, equals lambda times del g, and g is equal to constant k. The number lambda is called a Lagrange multiplier. Then you evaluate f at those points that you got from step A, and the largest is the maximum value and the smallest is the minimum value. So to see why this makes sense, how about we take a look at, let's say, the graph of g of x, y equals k in just 2 dimensions. And then we can imagine what it would look like in 3 dimensions. So here's y, here's x, put the origin over there, and I'll put some curve, let's say something like this. And this can be the curve g of x, y equals constant k. So there's only 2 variables I have to worry about, x and y, so I can plot it in the xy plane. Now how about we take a look at a function of x and y. So z equals f of x, y. Well then, we could always draw level curves in 2 dimensions to see what it would look like just in x and y. So how about I try drawing some level curves for f of x, y equals k. So I could do one kind of like that. Could do another level curve like this. So let's say this first one is hypothetically f of x, y equals, let's say, 7. Then the next one could be f of x, y equals 8. And these are all just slices of my surface f of x, y equals z. So I'll put another one at 9 and another one at 10, and how about I do one more at 11. So all of these correspond to constant z values. Okay, notice that if I want to know the maximum z value for subject to the constraint g of x, y equals k, then I should look at each of these level curves and see where the level curve with the biggest z value is, but is still intersecting with g of x, y equals k. So I discount this level curve because it doesn't intersect with g of x, y equals k, so it doesn't satisfy our constraint. It is a bigger value of z, but remember, for our problem, we are trying to find the biggest value of f, or in this case z, subject to the constraint g of x, y equals k. So it looks like the biggest value is actually this curve over here, f of x, y equals 10, that level curve. So it would seem like the biggest value of z should be 10, because all the other ones that intersect are smaller. So if I look at this point of intersection, it looks like the level curve just touches the constraint curve. So it looks like they share a tangent line, which means that they have the same normal line. And if they have the same normal line, then that means that they have gradients that are parallel to each other, because the gradient points in the direction of the normal line. So if the gradient of g is parallel to the gradient of f, then that means that the gradient of g is just some constant times the gradient of f. So that's basically our exact method of solving this thing. We just add an extra variable, we just add a z in there, and we just add a z in there, and that way we can just figure out what our gradient is for f, figure out what our gradient is for g, find lambda times that, because they'll just be parallel, so they're just scale versions of each other. And if we also consider the constraint g of x, y equals z equals k, then finding those values will help us find this level curve, basically, which will give us this z value that we want. So as an example, let's revisit example 6 from the previous section 14.7, where we have a rectangular box without a lid, and it's to be made from 12 square meters of cardboard. Let's find the maximum volume of such a box. So we have the volume V is equal to xyz, and we have our constraint G of xyz is the materials used to make the box. So that's 2xz plus 2yz plus xy equals 12. As we saw in the other example, it's just the surface area. Notice that we do not double the xy base because there's no lid, so there's only a bottom, not a top, whereas all the other sides are doubled. So now we need to look at the gradient of the volume, and that should equal some constant lambda times the gradient of G, where G is the constraint equal to 12. So if I have one gradient equal to lambda times another gradient, then that means that each of the components in that gradient vector are equal to each of these components times lambda. So the components of the gradient vector are just the partial derivatives. So that means that my partial derivative of v with respect to x must be lambda times the partial derivative of g with respect to x. And similarly, the partial derivative of v with respect to y must be lambda times gy, and partial derivative of v with respect to z must be lambda times gz. And I still have my constraint equation 2xz plus 2yz plus xy equals 12. So I have 4 equations to solve. Let's first figure out what these partials are, and these partials too. So partial v with respect to x, well, x is the only variable, so these guys are constant, so that's all I have left. So that's yz equals lambda times partial g with respect to x. So if I look at this with respect to x, that disappears. So all I have left is, it looks like 2z plus a y. Alright, I do the same thing for the partial v with respect to y. I should get xz. And then that would be lambda times partial g with respect to y, which is 2z plus x. Then I'll do that again for partial with respect to z. I should get xy equal to lambda times 2x plus 2y. And then I still have my constraint equation 2xz plus 2yz plus xy equals 12. Alright, solving these is never that straightforward. You always have to think outside the box, no pun intended, where you just come up with some kind of trick that'll hopefully either make some variables cancel or make everything equal each other so that you can figure out what one of the variables is and then figure out what the rest of them are. So in this case, I notice I've got yz, xz, and xy. So I can make all of these guys equal to each other pretty easily. I just have to multiply both sides of this equation by x, and then I get xyz equals lambda times 2z times x. So I'll write that as 2xz plus x times y. I have to distribute the x inside the parentheses. And in this case, this would be missing a y, so I'll multiply that by y. I get xyz equals lambda times 2yz plus xy. And then my last one is missing a z. So I'll multiply by z, and I get xyz equals lambda times 2xz plus 2yz. And I can't forget my constraint equation 2xz plus 2yz plus xy equals 12. So now solving the system is a little bit easier because all of these guys equal each other. So how about I take this and set it equal to this? because xyz equals xyz. Well, notice also that then I've got lambda on both sides, so I can just cancel and divide by lambda. There's no way that lambda equals 0, because if lambda equals 0, then that means that xyz equals 0, which means that this equals 0, but it's supposed to equal 12 for my constraint equation. So there's no way lambda is 0, so I can divide by it safely. So I'll set this equal to this, and I will get 2xz plus xy is equal to 2yz plus xy. Alright, so notice something cool. There's an xy on both sides, so I can cancel that. And I just get 2x equals 2yz, and then I can cancel the 2's. So I can just get xz equals yz. And there's no way that z is 0, because I've got a rectangular box. I don't want one of the dimensions to be 0. So that means that x is y. I mean, I'd have a volume of 0 then. Okay, so we figured out that x is y, so we've made some progress. How about we now set this equal to this? As before, lambda is 0, so I can divide by it. So I'll get 2yz plus xy is equal to 2xz plus 2yz. And then notice there's a 2yz on both sides, so I'll just cancel that. And I'll just end up with xy equals 2xz. And x can't be 0 for the same reason z can't be 0. None of the dimensions can be 0, so I could divide by that, and I just get that y is equal to 2z. So now I have x is equal to y, and y is equal to 2z. So that implies, well, I can use my constraint now. I haven't even used that yet. Notice, aside from the reasoning that lambda can't be 0. So I can take x and y, and I can replace them each with 2z. So I'll just substitute in for x, substitute in for y, substitute in for x, substitute in for y, just plug in 2z. So I'll get 4z squared plus 4z squared plus 4z squared equals 12, using my constraint equation. So that means that 4 plus 4 is 8, plus 4 is 12, so 12z squared equals 12. So z is plus or minus 1, but z can't be negative because it's the dimensions of a box, so z must be 1. And then x and y are 2z, so x is 2 and y is 2. And those are the same dimensions as we saw in section 14.7.6. So the maximum volume is just v equals 1 times 2 times 2, which is 4 cubic meters. Okay, how about we find the extreme values of the function f of xy equals x squared plus 2y squared on the circle x squared plus y squared equals 1. So this is our constraint this time. Notice we only have 2 variables, so that'll be a little bit easier to deal with. So we have del f equals lambda del g, same as before, and now g of xy, our constraint, is equal to 1. So we have all of the partials due to this, so we get the partial of f with respect to x equals lambda gx, and the partial of f with respect to y is lambda gy, and g of xy equals 1. So partial f with respect to x, well, that's just 2x because that's constant, and gx is just, again, 2x because that's constant, so that's wonderful. So I'll just write 2x times lambda. Then partial with respect to y, well, there's a 2 over there, so that's 4y. And then there's no 2 here, so that's just 2y. And I still have my constraint, x squared plus y squared equals 1. Alright, so this is the system I have to solve. But notice 2x equals 2x lambda. That's pretty easy to solve. In that case, either x is 0 and the whole thing is 0, or if x is not 0, we can divide by 2x on both sides to just get that lambda equals 1. So we got two possibilities. How about we look for when x is 0? So if x is 0, then that implies I could plug in 0 over there in our constraint. So I get y squared equals 1. So that means that y is plus or minus 1. How about if lambda is 1? That's my other possibility. Well, if lambda is 1, then I get 4y is 2y, so y is 0, so y is 0 over there, so x squared is 1. So that means that x is plus or minus 1 in that case. Okay, so that means that I have 4 different points. I've got f of 0, 1, which is 2. I've got f of 0 minus 1, which is 2. So that's when x is 0, but then I've also got when y is 0. So that's f of 1, 0, which is 1, and f of minus 1, 0, which is 1. So those are our candidates for the maximum minimum. Well, pretty clear that our maximum is over here and our minimum is over there. So I could say that f of 0 plus or minus 1 equals 2 is the max, and f of plus or minus 1, 0, which is 1, is the min. Alright, let's now find the extreme values of this function on the disk x squared plus y squared is less than or equal to 1. So it's almost the same as before, except that I'm looking at all of the points inside the disk included as part of my constraint. So that's different than the way that we did Lagrange. Lagrange helped us find all the values on the boundary of the disk, but not inside. But if you remember when we did the maximum minimum problems, finding the values on the boundary was the hard part anyway. Finding the values on the inside, we just look at the partial derivatives. So let's look at the partial with respect to x. Notice that's 2x. And the partial with respect to y is 4y. So those guys are 0 when x and y are 0. So that means that 0, 0 is the only critical point. Okay, so that means that we have our 4 points from before, and we have one additional point, f of 0, 0, inside. So I'll look at my boundary points, and I'll look at my point inside, and I'll see which is the max and which is the min. Well, it looks like I've got the same max as I did before on the boundary. F of 0 plus or minus 1 equals 2 is still the max. But since we're considering the domain inside of the circle 2 now, we now have f of 0, 0 equals 0 as the min. It's no longer on the boundary. So that's our minimum. Okay, let's find the points in the sphere x squared plus y squared plus z squared equals 4 that are closest to and farthest from the point 3, 1, minus 1. So the distance from a point x, y, z to the point 3, 1, minus 1 is x minus 3 squared plus y minus 1 squared plus z minus minus 1, which is z plus 1 squared, and then you take the square root. And as we've seen previously, minimizing this distance is the same as minimizing the square of the distance, so might as well just do that. I'll set d squared equal to our function that we're going to look at, f of x, y, z, and set that equal to x minus 3 squared plus y minus 1 squared plus z plus 1 squared, and that way we don't have to deal with the square root. Now we are subject to this constraint being on the sphere. So we'll set g of x, y, z equal to x squared plus y squared plus z squared equals 4. And we're looking at del f equals lambda del g, where g is 4. So it looks like my first equation, I'll take the partial for with respect to x of f, that's 2 times x minus 3, and that'll be 2x for the partial with respect to g times lambda. Similarly for y, I get 2 times y minus 1, that must be 2y times lambda, and then 2 times z plus 1 must be 2z times lambda, and I still have my constraint x squared plus y squared plus z squared equals 4. Okay, so dividing by 2 everywhere, I can simplify this a little bit. I get x minus 3 equals x times lambda. I get y minus 1 equals y times lambda. And I get z plus 1 equals z times lambda. And I'll just move all my x's to one side, so I get x times 1 minus lambda equals 3. Move my y's, so I'll get y times 1 minus lambda equals 1. Move my z's, so I get z times 1 minus lambda equals minus 1. All I did is move each of the variables over and factor. And then all I have to do is divide, and I get x is equal to 3 over 1 minus lambda. Y is equal to 1 over 1 minus lambda. And c is equal to minus 1 over 1 minus lambda. Notice it's impossible for lambda to be 1 and make this undefined, because then notice you would have, this is impossible. You can even see it more clearly over here. X minus 3 cannot equal x, nor can y minus 1 equal y, or z plus 1 equals z. So there's no way 1 equals lambda, so we're good to go. Now that we solve for x, y, and z, how about we plug those in to our constraint and see that they equal 4. So I'll take x squared, so that's 3 squared over 1 minus lambda squared. I'll set that plus y squared, which is 1 squared over 1 minus lambda squared. And then I'll add that to z squared, which is minus 1 squared over 1 minus lambda squared. And that must be 4. Okay, so this allows us to solve for lambda. This implies that 1 minus lambda squared must be 11 over 4. Notice we have 9, 1, and 1, so that's 11. So we can combine all of these because we have the same denominator. And 11 over 1 minus lambda squared equals 4. You just swap the 4 and the 1 minus lambda squared. So taking square roots, this gives us 1 minus lambda equals plus or minus the square root of 11 over 2, which means that I can move the 1 over, divide by the minus, so I get lambda equals 1 plus or minus the square root of 11 over 2. Okay, so this means that I get 2 different points. If I plug in 1 plus or minus square root of 11 over 2, I could plug that in for x, I could plug that in for y, plug that in for z, and I'll get 1 point as 6 over the square root of 11, 2 over the square root of 11, and minus 2 over the square root of 11. And I get that the other point is minus 6 over the square root of 11, minus 2 over the square root of 11, and 2 over the square root of 11. So one of these has got to be the closest and farthest. So how about we look at f, which was this thing over here. Notice that if I plug in 6 over the square root of 11, that's definitely going to be smaller than plugging in minus, because if I plug in the minus, I subtract 3, I get an even more negative number, and when I square it, the negative won't matter. Whereas if I plug in a positive, then the distance between that and 3 won't be as big. And the same logic applies to y minus 1, plugging in 2 over 11 versus negative 2 over rad 11. And then for the last term, z, plugging in the positive will definitely get me farther than plugging in the negative, because for the z term there's a positive. So it looks like this is my closest point, and this is my farthest. Alright, well, what if we had 2 constraints? If we had 2 constraints, we could still find the maximum values using a method of Lagrange multipliers, but we have to adjust it slightly. Notice in the case of 2 constraints, we're not looking at the intersection with level curves anymore. We're looking at the intersection with level surfaces. So in that case, I've got one gradient pointing away from the intersection of those level surfaces, and the other gradient from my other level surface, from my other constraint, pointing away. So that means that the plane that they construct must contain the gradient vector for f. So all we have to do is set the gradient equal to some scalar times our constraint g, and some scalar times our constraint h. So since we already used lambda, how about we use mu for the other scalar? And since we already used g for the first constraint, we'll use h for the second constraint. So now we have numbers lambda and mu are both called Lagrange multipliers. So as an example of this, how about we take a look at the maximum value of the function f of x, y, z equals x plus 2y plus 3z on the curve intersection of the plane x minus y plus z equals 1 and the cylinder x squared plus y squared equals 1. So we've got f of x, y, z equal to x plus 2y plus 3z, and we have 2 constraints. We've got g of x, y, z, whereas that is equal to x minus y plus z equals 1, and h of x, y, z, and that's equal to x squared plus y squared equals 1. And we want to look at del f equal to some constant lambda times del g plus some other constant mu times del h. So this gives us 3 equations for partials and 2 for constraints. So we have 1 equal to lambda, because when we take the partial of this with respect to x, notice these guys are constant, I just have 1. And when I take the partial g with respect to x, again, these guys are constant, I just have 1. So 1 times lambda, plus I have to remember to take the partial of this guy times mu. So that's going to be 2x times mu. So that wasn't too bad for the first one. Let's look at our second equation. That'll be partial with respect to y. Well, that's 2 for f, and then minus 1 for g. So minus 1 times lambda, so minus lambda, and then 2y for h, so 2y times mu. And then for my last one with respect to z, it looks like I've got 3 for f, and then I've got 1 for g, so 1 times lambda. And then there's no z for my third constraint, so that's wonderful. So I don't have any mu. I just get 3 equals lambda. Beautiful. I still have my constraints. I'll list those again. X minus y plus z equals 1, and x squared plus y squared equals 1. So I need to solve this system of 5 equations. But it doesn't look that bad because I already know that 3 is lambda. So how about I go and plug that into my first equation. So I can move the 3 over. I get minus 2 is 2x mu, so I'll write 2x mu is minus 2, and dividing by mu, I get that x is minus 1 over mu. And then I can do the same thing for y. I get 2y times mu is equal to 5 by plugging in lambda equals 3, just plus 3. And dividing, I get y is equal to 5 over 2 mu. Okay, so now let's solve this really quick by plugging into our constraint over there, because now I know what x and y are. So I can say that instead of x squared, I'll do minus 1 over mu squared, which is 1 over mu squared. The minus will cancel. And 5 over 2 mu becomes 25 over 4 mu squared. So that must be equal to 1. So that tells me that mu squared must be equal to 29 over 4 by multiplying this by 4 and then combining and then moving stuff over. So taking square roots, that gives me mu is equal to plus or minus the square root of 29 over 2. Okay, so I can take that and plug that back in to see what x and y are. I have to be a little bit careful though, because notice that for x, it's a minus. This is plus or minus. So whatever sign I choose for this guy, x must have the opposite sign, so I have to be careful of that. So if I make this plus, this has to be minus, and if I make this minus, this has to be plus. So in order to try to keep track of the difference in sign, I'll write that x is minus plus 2 over the square root of 29 to indicate that it's just whatever the opposite sign of this guy is. And then y is the same sign, there's no minus in there, so y is just plus or minus 5 over square root of 29. Okay, now I can get z because I know x minus y plus z equals 1, so z must be 1 minus x plus y, which is 1 plus or minus 7 over rad 29. Okay, so now I want to know what the maximum value of the function is, so I plug my x, y, and z into my function. So plugging in x, remember this is our function, so plugging in x we get minus plus 2 over the square root of 29 plus 2 times plus or minus 5 over the square root of 29 plus 3 times 1 plus or minus 7 over the square root of 29. And it looks like I've got, how about we start with the minus, so minus 2, and then this will be plus 10, and this is, I can distribute the 3, so if I just pull the 3 out, because it's not going to depend on the plus or minus, and the 3 times the plus 7 will be 21, so I have minus 2 plus 10 plus 21, so that's 29, and that's positive 29. So I'll say first I've got 3 plus the square root of 29, because notice if I have 29 in the numerator, then 29 over rad 29 could be rationalized, just becomes square root of 29. And what if I have the plus instead? So then I've got the minus, and I've got the minus. So it becomes the same thing, except that it'll be minus 29 on top. So that rationalizes to minus rad 29, so I get 3 plus or minus the square root of 29. So it looks like our maximum is just 3 plus the square root of 29.